So we have talked about the storage element. There is an additional component in the sequential circuit which is a storage element, and there are further two types of the memory elements, and we will discuss what those two types are, but we will be focusing only one of them. So there is one called the latch, which is the level sensitive devices, and the another one is flip-flop, in which the circuit operates on the edge. So level means the output appears only during the levels. It could be a positive level or it could be a negative level. It all depends on the designer, how designer is designing their circuit to operate. So these are called latches, which operates on the levels, and we have the positive edge triggered devices and negative edge triggered devices. They are called flip-flops. Okay, and latches are usually unstable. Why? Because during this entire period, the output of a circuit will keep changing. If you change the input, the output may instantly change, and it will keep fluctuating, whatever the value you are changing at the input. However, at the flip-flops, it reads the output only at the edge. Okay, it reads the output only at the edge, and if the input is changed, the next input change in the input will be reflected at the next edge of the clock. Okay, so the storage elements that operate with the signal's level rather than the edges are called latches, and those that operate on the edges are called flip-flops. Our focus on this discussion today is only on the flip-flops. And there are many different types of flip-flops, but I will be only discussing one of the types, which is D flip-flop, which is a very simple one. So D flip-flop usually represented with this kind of symbol. It has again digital circuitry inside it. To D corresponds to data. So again, please concentrate on this here. So whatever input we apply at D, it will be present at the output, which is labeled as Q. Okay, so this is the output, but it will be present at the output only at the next positive edge of the clock. I'll explain in details with the help of a waveform. But first look at the truth table. So when D is 0, Q will also be 0, but it says Qt plus 1. T plus 1 means T is the current instant, and plus 1 corresponds to the next positive edge of the clock. Okay, it is also referred as reset state. When the output is 0, it is called reset. When the output is 1, it is called set. So when you look at the waveforms diagram, so here D is this value, which is, first of all, it is 0, it is 1, and it is 0 again. Before I explain this waveform, I'd like to ask you, do you understand the representation of a signal in these waveforms, zeros and ones? So we have been talking about registers so far. So registers are 32 bits wide. Okay, so for example, if I have let's say if I have a 32-bit value, any value, let's say random. Okay, so let's say this is 32, or let's say 64-bit value. Each value actually represent a signal of wire. It could be 0 or 1. So when it is 0, it means that if we have multiple wires, so this value is 0, and when it is set to 1, it will be like this, and then 1 0, and like this. Okay, so if you have to transmit a 32-bit value from, for example, from one end to another end, the 32-bit value or a 64-bit value, do you think we should have 32 wires or 64 wires? Have you ever imagined about this USB cable? How many wires in there? Each wire represents one signal. It could, each wire can have either a voltage 5 volt or a 0 volt. Previously, in the previous computers, like old computer, we used to have a parallel port which has like 25 different wires, which means that you could transmit 25 bits data all in parallel. But it turns out that we cannot actually have bigger size of the connectors because it makes the a component bulky. So that's why this universal serial bus was invented. Here there are only 4 wires in serial bus, no matter whatever the whatever kind of port you are using, if it is a USB-C port or simple USB port. It's just Mac or Apple which keeps on changing their connector shapes, but everything is inside is same. Okay, so there are 4 wires only. So one is VCC, which is the power, and the other one is ground, and there are 2 wires in between, which is D positive and D negative. D positive means for transmitting data, D negative is receiving the data, and it transfers the data at a rate of USB 3.0, which is the standard, current standard. It transfers the data at a rate of 5 gigabits per second. So you can imagine the 5 gigabits of value are being transmitted per second according to these protocols. Okay, so what I'm trying to say is, if we have a 32-bit value, if I have to transmit this data from, let's say, it's my this data is stored in a memory, and I have to transfer it into register on a processor. Okay, so this would transmit it like this would be 0, and then 0, and this would be 1, and then this would be 0 again, and this is 1, and then this is 0, sorry, this one, and then 1, 1, 1 for 3 times, and then 0, 0. This is how the data is transmitted. Okay, so when you see a waveform like this, you can easily translate it into number of bits: 0, 0, 1, sorry, 1, 0, 1, 0, and 1, 1, 1, and so on. Okay, any question? Okay, good. So what we are saying here is, you see a value of D, it keeps on changing from 0 to 1, and you see this change in the input at D is reflected at the output Q only at the positive edge of the clock. Okay, again, look, the D value is changed at this instant of time. Okay, at this instant of time D value is changed, but it is not reflected at the output. Q is still the same. It changes when the clock positive edge, next positive edge of the clock comes in. Okay, so when the positive edge of the clock comes in, this flip-flop reads the value of D and reflects it at the output after a certain delay. I'll be talking about this delay shortly. Get it? Similarly, D value is changed here at this instant of time, but this input change is not reflected at the output instantly. It does not reflect instantly. It waits for the next positive edge of the clock to come in and then reflect the change in the input at the output. Okay? Are you following? Do you want me to repeat? Feel free to. Okay. So this is D input. You see, I have changed the input. So for example, here I changed the input from 0 to 1. Okay, so practically speaking, this input should reflect at the output Q instantly. Okay, but it does not instantly reflect it because it is synchronized with the clock. So when I change the input from 0 to 1, it did not reflect here at the output. This is the waveform of the Q. Okay, it is still showing 0. When the next positive edge of the clock strike, it reads the data. This flip-flop reads the data, whatever the input data is, it is 1, so it reflects it at Q, not instantly, after a certain delay. I'll talk about that delay shortly. Okay. Similarly, when the D is changed to 0, at any instant of time we can change the input, but the output does not reflect instantly. It is synchronized with the positive edge of the clock. Okay, so when the next positive edge of the clock comes in, then D is changed from, Q is changed from 1 to 0 because the D value was changed to 0. So this is the simplest form of any flip-flop, where whatever you put at the input, it is reflected at the output, only at the positive edge of the clock. Okay? So D changes but does not change the Q here. This I already have explained. So this is how, first of all, the activities in a computer are synchronized because of these clock edges, positive clock edge. It's up to the designer also. They can make the circuit synchronize either on the positive edge of the clock or the negative edge of the clock. Okay, but the entire circuit should work on the same clock edge. Some more complex circuits work independently on different clock edges. Okay, and as I said that we will be using only this high-level description, high-level symbolic representation of D flip-flop. Inside it, it has a circuit components like this. We're not going into the details of how this works, but you are already familiar with these gates. Okay. Now there is another thing: setup time, hold time, and the propagation delay. So I actually to wake up you guys, I need a volunteer here just to demonstrate of how the clock works and what is the difference between setup time, hold time, and the propagation delay. Okay, you want to come in? Good. Olivier, thanks. So first of all, you have to play two roles, okay? One is the role of a clock, and how do you demonstrate a clock? You will keep rotating your neck, okay? You'll keep turning your neck around like this, and we can assume that when you look here in front of the class, it is acting like at the positive edge of the clock, okay? And your activity is you will read the data at the positive edge of the clock, and once you read it, you have to produce an output. And in the output, whatever I show you, you have to write it on the board, okay? So just keep rotating your head. It's just a mimicry of a clock. Yeah, just keep looking like this, and we will consider it as like positive edge of the clock, and this is your complete clock cycle period. Keep doing it. Start doing. You have to keep rotating or keep moving your head like this, and this is just a depiction of how the clock signals keep moving. Just keep doing it. Yeah, turn around also. Not not completely. You just stand still. Look at me. Just stand still, okay? And keep moving your head like this, and then turn back and keep doing that. Okay? Okay? Don't move your body and just keep doing it. Okay? Now I have to provide you a data, okay, which you can only read when you look here, which is the positive edge of the clock. Okay? And once you read it, what you're supposed to be doing, you have to produce at the output. Output is board. You can just write it on the board, okay, whatever I give you. Okay, just keep moving. Keep moving. How about reducing the cycle time? What do you think? What immediate effect you will see? You should go fast, right? Okay, I'm not reducing it. Okay, so first of all, when I give you, keep moving. You are not supposed to be stopped. Okay. Okay. All right. So I have to provide the input. Okay, I have to provide the data input. Okay. No, you're cheating now. You cannot do it like this. Okay, just stand still, stay your body, only move your neck. That's it. Yes, that is the clock cycle. I'll give you 0.5 bonus points for this activity, okay? All right, okay, so just keep moving your head. So now I'm giving the input data to him. Keep moving. I'm giving the input data to him. You have to just keep looking, also look at here. So I cannot just provide, I cannot just provide the data at any instant of time, okay? When I provide him the data, when he's looking at here, at this instant of time, which means the positive edge of the clock, he cannot grab the data immediately. So which means that I cannot provide the data right at the positive edge of the clock. I cannot provide the data right at this point. I have to make the data available way before the positive edge of the clock strikes. so that the data becomes stable, and when the positive edge of the clock comes in, the data can be read properly. Okay? Start moving again. I have already provided data. Now you can read whatever is written. Once you read it, go and write it on the board. Yeah, write it on the board. You have the marker there. Yep, whatever. So he read the data, right? And he went at the output. That is called the processing time. And the delay after reading the data and producing at the output is called the propagation delay. Okay? That is the input data is propagated at the output. Okay? Thank you very much, Olivia. I appreciate it. You'll get 0.5% bonus. The next time when I call for volunteer, you guys know what to do. Okay. And then, yeah, have a question?
So I understand that propagation time concept and what the setup time is. Is there some minimum amount of time that you have to like set up before the clock reads it, or is it just essentially any time before the clock reads it?
No, it's a specific time that we need to keep on holding the data until the next clock edge strikes. It depends on the designer. It depends on the hardware component that we have used. So they actually, while designing the circuit, they actually calculate a very minute delays of every single component. And based on this component, the circuit components, they calculate how much time should be, before how much time the data should be made available before the next clock edge. Okay? And another thing is, you cannot just provide the data at the positive edge of the clock and you cannot just instantly remove it. It has to remain there, and that is what we call the hold time. Because if you just remove it immediately, you might not be able to read the data properly. Okay? So setup time is the time which is required for the data to be available before the next positive edge of the clock. Hold time, we need to hold the data for a certain period of time, and the propagation delay is when the data is read, there is a delay in producing the output, and that delay is caused by the internal circuitry. Okay? Because you have multiple AND gates, OR gates, the data is passed through the AND gates, so there is a delay for the AND gates and OR gates. So that delay is called the propagation delay. It is not like you apply the input and the output is immediately produced. Okay, there is always a delay, but that delay is within nanoseconds. So for the time-sensitive applications, that delay matters a lot. But if you just apply an input and you'll immediately see an output, there is always a delay. Yeah, you were asking a question, yeah.
Why is the hold time more than the propagation delay?
So hold time, it actually depicts that you should not remove the input before the output is produced. Okay, before the output is reflected, before this input change is reflected at the output. Once it is reflected on the output, you can safely remove the data or change the data. Okay. But to make things easier, we can consider having a propagation delay 0, which means that as soon as you apply the input, the output is immediately produced. Okay, this amount is very like in femtoseconds sometimes, 10 to the power minus 12. Okay. All right, so D flip-flop is used to hold a bit of information. So out of 32 registers or 32-bit registers, one D flip-flop will be used to hold 1 bit of that 32-bit value. Okay, and you can imagine how complex the circuitry could get. D flip-flop has itself multiple number of logic gates.